Hello everyone, my name is Henry London, and I am a member of the Hansen Research Group. I'm here to talk to you about a recent publication in Applied Energy Materials called Modulating Excited State Lifetimes in Copper-1 Complexes, the Role of Surface Binding Motifs. For this, we designed 3 different copper complexes with carboxylic acid functionalized phenylpyridinyl methylamine ligands. We picked these because these copper complexes are known to absorb in the visible light region and undergo metal-to-ligand charge transfer, creating this nice reactive excited state. Unfortunately, when it's in this excited state, it likes to undergo ion-Teller distortion, distorting the molecule from tetrahedral to square planar, thus decreasing our reactivity and decreasing our excited state lifetime. To get around this, people have tried interlocking the superstructure of the molecule or creating enough steric bulk to make it unfavorable. Both of these tactics work, but are synthetically difficult and can limit access to the reactive center. Our strategy is to take all 3 molecules and bind them to the surface. By binding them to the surface, we hope to inhibit this distortion, thus increasing our excited state lifetime and our reactivity. To test the effect of the rigidity and surface binding, we designed molecule 1 to be nice and rigid and bind through both ligands to limit distortion as much as possible, while complex 2 was designed with an extended chain, allowing for greater flexibility to allow it to distort some, but still be bound to the surface to limit it. While complex 3 was designed to only bind through one ligand, keeping one ligand immobilized while letting the other one move freely. So once we bound them to the surface, we have to investigate our complexes and make sure that they're bound to the surface and make sure that we know the impact on ground state electronics. These complexes have a minimum impact on ground state electronics, so we then investigated them through FTIR. We looked at the binding site motifs by looking at the carboxylic acid peaks, and we noticed that whenever we bound them to a surface, our carboxylic acid peaks decreased greatly, indicating that they were binding through the carboxylic acids. So we then investigated using transient absorption. We started by investigating our complexes in methanol, and what we found is that there was a ground state bleach followed by a excited state absorption. This is consistent with copper complexes going from singlet metal ligand charge transfer to triplet metal ligand charge transfer states. We then investigated our complexes on surface, and we found a minimal impact on the excited state features for OTA. But we see a vast impact on the excited state lifetimes of our complexes. So, our complex 1, in solution, it had a 21 picosecond lifetime. When we loaded on the surface, we saw a 17-fold increase in our excited state lifetime. While for complex 2 and 3, we only saw a 7-fold increase, likely due to them being able to distort more easily than complex 1, which is rigidly bound to the surface. We then compared our complexes on the surface to our complexes in suspended in a solid solution, in this case PMMA, and we found that when complex 1 is most similar to our solid solution data, thus indicating that that increase in lifetime is likely due to the decrease in distortion. We then investigated our complexes for solar cells. Unfortunately, they are not competitive with commercially available options. However, we did see that complex 1 bound to the surface had better solar cell properties than our complex 3, which bound only through one ligand, indicating that this rigid binding does actually improve our solar cell data. However, complex 2 does not exceed our detection limit, and this is likely due to that extended chain making electron transfer less favorable. So, in conclusion, relative to solution, the excited state lifetime for zirconium oxide bound complexes increase in the order of 2 and 3 by 7-fold, while one is a 17-fold increase. We attribute this increase in lifetime to the inhibition of that planarizing distortion, and the largest change being when they were tightly bound versus the more flexible or singly bound, supports the idea that if we rigidify it, we're able to limit the distortion to a greater extent. This also indicates that we could use this as an effective strategy for other molecules inhibiting undesirable molecular distortion. Thus, we can then apply what we learned and use it as a strategy to extend the excited state lifetime and reactivity for complexes going into OLEDs or into light harvesting applications, or even for photocatalytic applications. If you would like to know more, please check out the full paper at Applied Energy Materials. Follow the DOI listed below, and I appreciate you listening to this. Thank you.